As for the addition of collinear vectors, let us consider collinear vectors having the same direction as shown in the following figure. So two forces, F1 of magnitude 5 Newton, which is horizontal to the right, and another force F2, which is of magnitude 3 Newton horizontally also to the right. In order to find the resultant force of these two forces, we have to add F1 and F2. Why plus F1 plus F2? Because by convention, the positive sense of horizontal direction is to the right. So these two forces are directed in the positive sense of the conventional positive direction. So that's why we say that plus F1 plus F2. Fr then is equal to 5 Newton plus 3 Newton, which is equal to 8 Newton. So this is the resultant force of two forces. They sum up together. And if I want to write it in the vector form, I have to write Fr vector equal 8I vector. However, considering opposite forces, opposite collinear vectors, such as these shown in this diagram, we have F1 of magnitude 6 Newton, which is horizontal to the right, and F2, which is equal to 3 Newton, horizontal to the left, so they have opposite directions. They're not going to sum up. One is going to not cancel, but to decrease to result in a less resultant force. How can we do that? We have to check. F1 is in the positive sense, so we write a plus F1. F2 is in the negative sense, so we write minus F2. The resultant force is 6 minus 3, which is 3 Newton. Since we obtained it in the positive value, so this means that the resultant force is going to be in the positive sense, as shown in this figure. Fr is equal to 3 Newton. If the opposite was true, and if we had F1 equal 3 Newton and F2 equal 6 Newton, then we should have obtained a negative value, which means that the resultant force is going to be in the negative direction, and this is actually logical, since the one which is stronger is going to be the other one. Now, addition of non-collinear vectors. The first method used is projection method. So dealing with a force vector, which is uh, two-dimensional, any vector represented in 2D orthonormal system can be expressed in terms of two components, x component, which means horizontal, and the y component, which is vertical. In the adjacent figure, consider the blue vector to be the force vector. It is the force vector uh, studied. The red vector is said to be the x component of f, which is projection of f on x-axis. We take the top of the vector and draw perpendicular projection to the x-axis. The distance between the foot of this projection and the origin of the force is represents the horizontal component or the x component of f. And taking the top of the force vector, drawing an orthogonal projection to the y-axis. Distance between the foot and the origin of the force is the y component of this force. So we write that f any vector in the two-dimensional reference system is expressed in terms of its x component and y component. So f vector is equal to fx I vector plus fy j vector, and the magnitude of f is radical fx squared plus fy squared. In order to prove that f is equal to radical fx squared plus fy squared, and by f here we mean the magnitude, we can do some geometric calculations or proofs. We have, knowing that the angle formed between the force vector f and the x-axis is beta. So in this right triangle, applying the trigonometric relations, cosine beta is equal to the adjacent over the hypotenuse. So cosine beta is fx over f as a magnitude. Then doing a cross multiplication, we get that fx is equal to f cosine beta. Similarly, in this right triangle, if this is beta, then this is beta, since they form a z